Now, if y'all don't know Franco, he's a physicist that works at CERN, which I think he says is different than a CERN physicist. Anyway, comes around on Flat Earth Fridays, engages in some of the conversations, has a lot of history in the physics, decades. We appreciate people bringing their value and their PhDs and their credentials and having the discussions. And there's been a couple that's pulled up throughout the few dozen episodes, right? Anywhere from astrophysicists to nuclear physicists. I think Franco is a particle physicist. There's a few of those guys that have some history in the sciences. Which one do you think utilizes their background for the most value with the conversation? And Franco was nominated and the people voted for him. So congratulations, Franco. You won a Platinum Plan Award for being the least likely to waste a PhD. Shout out to you, bro. Do you want to say anything about the award? I mean, you came to grab the mic, so.
No, no, thanks. I prefer not because I wouldn't want to be tapped again into fightings and things like that. I wouldn't want that. So thank you. And okay.
So you mean in all these episodes, you can't think of one positive interaction you've had in here, Franco? The hours you've spent in here, you can't think of one time where you laughed at an inappropriate joke or you laughed at a physics joke or nothing of the sort? It's all negative to you?
No, I didn't say that. I said I didn't want to start the discussion because I know how it ends most of the times. And I even got nominated for that. Thank you for raging and storming off and some things like that. So I wouldn't want that to happen again. So that's why I wouldn't want to discuss this. Yeah, I've had no, I wouldn't say positive. Some non-negative experiences when I was asked genuine questions. That was and without without people. Trying to I wouldn't know how to say it to jump in and spoil it, but okay.
I got a question for you, Franco.
Okay.
If you don't mind.
No, I don't mind questions.
Like, what is the progress of CERN? Is it accomplishing its goals as of today?
Well, its goals are to investigate, and so yes, the investigation is going on multiple subjects, and so I would say it is.
And what are some of the main subjects that it's investigating? I mean, I know that might be a lame question, but it's something I would be interested in knowing.
Well, it's everything about fundamental physics. So, investigating, for instance, in the LHC, that's the part I'm involved with. It's about testing the current theory and seeing whether its predictions are fulfilled, and maybe investigating for new physics in the fundamental area. Then there are other experiments going on, like on antimatter and things like that. But I'm aware of everything that's going on there. There's a very high number of experiments going on. So, but they're all about fundamental physics.
That's what we're told.
And so the theory about the I think you say antimatters, is that like the black matters? Is that kind of what that is? Because the little bit that I read on it, I don't want to say it's been conspiratorial, but I just didn't get the full scope. Because when I try to find information, I investigate both sides. I try to, and so from what I heard was that it was investigating black matter and trying to find portals into the regions of hell. If I'm incorrect, please, correct me, into the portals of hell, and trying to bring matter or actual people or things back from those holes, and using the CERN a technology. That's what they were trying to do. Is that correct, or is that just something that is made up?
No, it's made up. I'm sorry, no portals and things like that.
Okay. Yeah, I'm just asking, brother. I don't really know that.
No. Okay.
Okay, that's good. I just wanted to know what are they doing with that CERN other than what you're saying? Is there any other things that they're bringing about that people don't know about?
Well, I don't know what you mean by people don't know about, because of course it's fundamental physics, and it's not like everybody knows about this, and it's personally I don't even know about all the experiments that are going on. There are many, but they're all about fundamental physics. That's the purpose of the organization, and that. It's not just one experiment. But then what happens when you try to explain this and popularize this on media and so on, especially because many times you want to make clickbait titles and so on. People are using, especially journalists and people like that, are using big words and big sounding words, which are meant to impress people. And so that's why then everything gets misunderstood or improperly used or whatever.
Okay. That makes sense.
For instance, a few months ago, there was this. CERN scientists have discovered this 4-dimensional entity lurking in acceleration. It's totally bullshit.
Right. Bullshit.
Because it was. Well, I read the article, and what it was about was. I mean, it's the same degree of 4-dimensionality as a roulette ball in a rolling about in a cone, right? It's something like that. It's actually 2-dimensional thing, and it's not. It's a mathematical structure. It's nothing to do with extra-dimensional beings lurking. It's just mathematical stuff. So. It's no more 4D than a billiard ball, no, on a billiard. So.
Did you ever find, Witsit was wondering if you ever found the virtual photon?
If it was, what about the virtual photon?
Do you use a virtual experiment to find the virtual photon?
Well, you don't find virtual photons. You use them to explain what you see. Not just virtual photons, but all sorts of virtual particles. Virtual particles are part of quantum field theory, so they're just part of that formalism. There's not just photons.
Is it an explanation though?
So it is kind of like a virtual experiment, kind of in that case, then, huh? It's not a real experiment. It's just like
no, it's not.
It's a mathematical simulated experiment that quantifies their existence.
No, it's not that.
So you have an experiment then that quantifies their existence.
You have an experiment which quantifies the prediction of your theory. The theory involves virtual particles as an explanation of what's going on. But by definition, you cannot see virtual particles. They're just what happens between the initial and final state.
So, like, let's say I make a prediction about something.
Yeah.
And then in order to explain my prediction, I have to start invoking other things that I can't measure. I can't do experimentation to prove them. I just say, well, those have to be there in order to make this previous assertion that I made. Those have to be there to make that true.
Yeah.
So then they must be there. Do you kind of see how that's a little bit of a fallacious position to branch a whole, like, whole branch of physics on?
No, because you can use these things to make a prediction. You verify the prediction, and that's it.
And create more magical bullshit, and more paradoxes, and endless open questions.
Not true.
So it's basically quantum physics, dark matter. Okay, so everyone knows what it actually is. Their physics and equations within their particle physics models don't actually match the observations and fluctuations that they see on the quantum scale. So they backfill the equations with a mathematical construct called virtual photons, just like how on the cosmological scale they fit dark matter into the equations to make the math work. It's just a conceptual mathematical construct that they reify because their models don't match observation.
I just followed yesterday a seminar here, actually a series of 3 lectures here by a professor, retired professor, theoretical physicist here in Pisa. But it was explaining the standard model to philosophy students and to physics students, and he defined in effect a successful theory as a theory which is synthetic in that the number of parameters, of free parameters that you have to introduce in a theory is way lower than the number of observations it explains. And this is true for the standard model. The number of hypotheses and the number of the sheer number of parameters, like 19 parameters in the standard model that you have to introduce, they are way less than the thousands of explained observations which are there. So it's not like you are reifying something because it doesn't match observation. It matches observation at an incredible degree. Like, for instance, as it was shown yesterday again, the prediction on the anomalous magnetic moment of the electron, which has a prediction, precision on the prediction of less than 1 part per billion, which is incredible, both experimentally and theoretically, and the predictions agree, which is an incredible success for a theory.
No, this is what they always do. They always take the part that disproves their theory, and then they claim it proves it. It's crazy. It's like pure wizardry. So it's like saying, we saw how fast these galaxies were moving, and we know the gravitational force that's required. Oh, boom, we were able to perfectly and precisely predict the amount of dark matter there. See, what virtual photons actually are is, you called it an anomalous magnetic moment. It's that the electromagnetic force that holds everything together, right? Like, there has to be some intermediary, quote unquote, particle in your paradigm because your math doesn't work. So now that you've found out where your math doesn't work and how there's a missing component, yeah, of course, you can predict it with precision going forward, right? So to quote, I forgot his name, but Richard Dawkins, no, not Richard Dawkins, whoever the other guy is, one of your heroes, he says that virtual photons don't actually exist, right? Their existence is questionable at best. They're just a construct we use to make the equations balance out. They've never been the input or output of any experiment. So you're going to point out that now that we found out that electromagnetism doesn't work in our particle physics model, so we created a new particle, and now we've given it a mathematical value. Now we can make predictions going forward, meaning where we know there's going to be the electromagnetic force, we can predict the amount of quote-unquote virtual photons because we know how much our particle will be wrong without it. That doesn't prove virtual photons exist. It just further substantiates that your model sucks.
No, it's not my definition that a model sucks if it predicts things and it predicts thousands of observations with an incredible prediction. That is the definition of a model. I don't know what you think, what you mean, but the fact is that from the 1940s on, every prediction of quantum electrodynamics is fulfilled. So it works. I don't care if you don't believe in virtual photons. They are the current description, and the current description is incredibly working, especially the QED part. And that's precisely a definition of successful model. I don't care if you, I'm sorry, I don't care if you don't believe it, because the whole of the science community believes it, and it works, it matches prediction. That's all we care about. If you have something that doesn't match, then we investigate it and we try to refine the model. As I was hearing yesterday, this theoretical physicist explain, we still have theoretical physicists still have some trouble with refining the so-called standard model, which has incredible success, but still has some parts which are not satisfactory, and that's why people are investigating the beyond standard model thing. This guy, I can tell you his name, is Professor Riccardo Barbieri. He told the students that he graduated in 69, and he went to CERN in 1973. And from 1973, which was the year that the standard model was established, he has worked on the beyond the standard model physics. He has tried to extend it. He has tried to sort of I wouldn't say falsify it, but just to find something beyond that. He's worked all his life on this, and he still says that that's the best thing we have so far, and it's very satisfactory. Still, it has some unsatisfactory points on a theoretical point of view, but from the point of view of description of reality, he said it is the best synthetic theory that we have at the moment. So I'm sorry.
So your argument is that a physicist says that he thinks it's the best that he can come up with so far. Like, I don't care about that.
No, I'm saying the whole community of hundreds of thousands of physicists for the past 100 years. If you don't agree with that, it's your problem.
No, that's objectively not true. Don't interrupt me, man.
Is AI helping?
So
that's why I didn't want to discuss.
Richard Feynman.
I'm sorry.
Richard
I'm sorry. That's why I didn't want to jump in.
I know, because you want to try to flex your PhD without getting called out. So Richard Feynman is the guy that I was talking about, okay? And he explains it very simply. He didn't believe in them. He said, we know they don't exist. He said they're not the input or output of any experiment ever. Their existence is questionable at best. Our equation just didn't work. So we had to come up with something to backfill our equations to make the math work. That's Richard Feynman. That isn't just some random guy. Okay,
Richard Feynman got the Nobel
I don't care
Prize.
about your appeal to consensus. I don't care about your reification fallacy. I don't care about your arbitrary subjective. It's the best we have right now. It's the best you have right now because you believe in particle physics and you have a materialistic confinement. So you quantify everything on the quantum scale. So you need them to exist because your model sucks. Okay, the fact that we keep on seeing it happen is proof your model's wrong. It's like someone saying dark matter proves gravity's true. That's ridiculous. It's circular. It's a reification fallacy. Virtual photons don't exist. You started off by saying, oh, well, they don't actually exist. They're just a construct. Then you went on talking about how they're reality and we know they exist. You're just double speaking.
Richard Feynman got the Nobel Prize for developing QED with virtual photons. So I don't care if you say he believed it doesn't exist. He believed something he created, got the Nobel Prize for, do not exist. Maybe it's a philosophical thing. You like philosophical fallacies and things like this. I don't know. I don't care. What the problem, the fact is that this is the current model we have. And the model we have works. I'm sorry for you. You don't believe it.
It sounds like a religion, dude. This sounds like a...
Okay,
like,
but it works.
This is like the Catholic Church saying this is the current doctrine we have. Sorry if you don't believe it. Like, think about the point. I just brought up the best guy I could bring up, right? You just admitted Richard Feynman came up with it. He got a Nobel Prize in QED, that's quantum electrodynamics for people that don't know. He's the whole reason you can even talk about virtual photons. And he explained to the world what they are. And you know what he said? That they don't exist. They're just a concept because our equations don't work. The reason he got his Nobel Prize is similar to the reason that everyone touts Einstein's a genius, because no one could explain it and your model had been disproven until someone else came in and made up a new mathematical concept to make the math work again. So they're like, yeah, you saved us. Now we don't have to admit our religious dogma isn't true. We can keep running around claiming it's true. So Richard Feynman explains it point blank. I'm going to quote it again. They've never been the input or output of any experiment. Their existence is questionable at best. They're just a mathematical concept to make our equations work because they weren't working.
Mic drop.
I don't know what to, I don't know what to reply to this, because it will always be like this. When you come up with a model with virtual whatever, or not reification and non-fallacious model, which explains the number of experimental observation that we do currently do, then we can discuss this. The purpose of physics is this: finding a model, a mathematical model. The thing that Feynman said is that the equations were not working. We changed them. We have a new model, and the new model describes things. That's the fact. You don't have to use the popularization and the conferences that Feynman used. You have to read the papers. You have to read the scientific papers, and the scientific papers is what the Nobel Prize was based on, not the conferences where people laughed without understanding what he was saying. I've heard some of them. By the way, Feynman believed that the Earth was a globe and the gravity worked.
I don't care what
I don't care what you think
about the Earth being a globe. Think about this. Your argument is fundamentally. Listen, Franco. You don't got to get all worked up, man. Your argument's fundamentally fallacious. Okay. You're saying that this is the best.
I didn't want to discuss.
I know you wanted. You didn't want me to call you out. That's why I popped up. I couldn't listen to you try to flex like you were talking about something in reality. You're not. Okay. This is all fake pseudoscience. This is all fake pseudoscience. Good.
I have a question for him. I just don't want him to rage quit. Go ahead.
Fake pseudoscience is bringing to you the device you're typing in and speaking in.
All right, Frank, let's take it back. I don't want you to get mad and leave. I'm not trying to fight with you. I just want the audience to know, because it seems like oftentimes people come in with credentials and they kind of flex their credentials and they leave the other side of the story out. So what you're doing would be similar to an astronomer coming in here talking about how we know dark matter exists. And sure, we don't know what it is. Sure, it's just math. Sure, our equations didn't match reality, so we had to just plug in dark matter. But until you come up with the better theory, all the physicists agree, all the astronomers agree that dark matter exists. That's just fallacious. That doesn't make it real. It's just math. And you're treating that concept, that abstraction, as if it's concrete, which is a reification fallacy, and falsifications independent of replacement. And further, I can replace it. An etheric model automatically has that intermediary interaction covered intrinsically. If you have a fluid background medium akin to an ether, right? An oscillatory fluid background medium, and these are emergent properties, you have an intermediary interaction automatically. You don't have that, though, because you don't have an ether and you have particle physics. So you had to put a new particle in between the electromagnetic interactions to somehow explain why the math wasn't working. And the main problem here is because you said science, we have to be able to mathematically, we have to have the math to explain it. So that's the problem. You guys are materialists. You think you have to be able to quantify it or it doesn't exist. But you cannot quantify the immaterial. You cannot quantify the ether. So now you guys just ignore reality and make up concepts and reify them. So do you see that, for one, falsifications independent of replacement, and two, we do have a significantly more viable option. It's an etheric medium that's in the background that would automatically have the intermediary interaction covered.
Okay, when I see the equations for that, I will believe it.
That's what I'm saying. They need the math.
For fuck's sake.
One more question, Franco. Can you quantify the immaterial?
But the problem is that science is quantitative. Physics is a quantitative. It's philosophy that is just about words. You have a philosophical a theory about ether. Okay. The problem is that science is something else. Science, especially physics, is something that wants quantitative predictions. And unless you do that, your words are useless in physics. They can be satisfactory for philosophy, they can be satisfactory for religion, they cannot be satisfactory for physics, because physics wants quantitative things. You want to be able to build things, to have.
I agree.
number.
We
If you have
I
numbers,
actually agree with you.
then you can compare with observations, with measurements. Measurements coming with an error and precision and accuracy, and you want to compare the numerical predictions of your theory with the numerical result of your experiment within errors.
Look, I'm going to meet you in the middle, Frank. I'm going to meet you in the middle. I agree with you that the ability to quantify it is extremely important because that's how we're able to replicate it and create technologies, right? That's how we're able to do experiments and make technologies because we have to be able to replicate it. In order to be able to replicate it with precision, we have to be able to quantify it. I have no problem with the quantification. I don't even have a problem with you doing your equations and using the virtual photon variable because that's, like you said, that we were able to actually attain immensely precise, quote unquote, predictive capability. It's really post-diction. After that, that's cool. The problem is the actual interpretation. See, science explains things, math describes things. So in physics and science, we're explaining what's actually happening in reality. Then we come back around and we want to describe that explanation with math so we can apply it. The problem is that your field is conflating the two, calling math science, and then treating the math as if it's a real thing and giving it concreteness. So you're actually conflating the conceptual math with what's really happening. Okay, so it's the interpretation that is the problem, and that's why you guys are still stuck 50 years later, because you guys don't seem to understand that. Do you see the point that I'm making to you? Science explains, math describes.
No, because math describes what is being observed and predicts what you're going to observe, and then you check and you guess and you see what happens. You want to do I have to show you the standard model prediction for the mass of the top quark before it was discovered? LEP accelerator, which I worked for in the 90s, actually predicted. And it was via virtual processes where the top quark intervened as a virtual particle in what was measured, its mass. The interval for the predicted mass of the top quark was restricted before 1995 when it actually was discovered at Tevatron. And it was exactly what the LEP had predicted it to be, numerically. And it was there and it was discovered. Now you may say that it's not there and people have made things up and the top quark does not exist. But this is what we measured. And it was exactly what it was predicted. Then the Higgs boson was predicted. And again, the interval for the allowed mass of the Higgs mass was restricted by previous experiments. And then it was found at 125 JeV. And then all the couplings to all the fermions that the Higgs couples to, they have been measured at LHC and they are exactly where they were predicted to be. So this is something that was before, not a prediction, it's a prediction, and it matches the theory mathematically. And
I already explained why, though. Okay, you're actually skating past my point. You're skating past my point, bro.
Okay.
This is just like the electron. Okay, the electron. We can mathematically describe the phenomenon referred to as an electron with immense precision to the point that we have circuit boards and computers and all kinds of technology. We shouldn't just throw those equations out. That's what we use to make all semiconductors. We use the parametric down conversion equation to make semiconductors. We shouldn't just throw the equations out. But that doesn't mean that your interpretation of the electron, because we had to quantify it, so we had to count it. That's what quantum physics is. It comes from the German word quanta, meaning to count. So we had to count the phenomenon called...
It comes from Latin quantum. It's Latin. Quantum is Latin, Russell.
Okay, fair. Well, I think it's the German word that means to count, though. I don't think in Latin it means to count. Yes. I could be wrong, actually. I don't know. It doesn't matter. Quantum, quantify, they want to count things. And it's useful to count things. I would actually say quantum is like one of the most precise fields of science ever. Right? It is. But it's also flooded with pseudoscience because they're conflating math with what science is, which is to explain things. And I don't want to go into circles with you. Obviously, you're not going to concede to me because I guess it would be like, oh, this college drop, I can't concede to him. It's whatever. With the analogy with the electron, it's like we were like, okay, we have to conceptualize an electron being in a physical space so we can count it. Well, now we've been like, oh, we're going to change what it is. Now it's just in a distribution cloud, and maybe it's in this general area, right? But the initial interpretation of it was wrong. The current interpretation of it's wrong, but we still have to be able to count it. It's the same thing with this. The virtual photon doesn't exist. So this is all I'm going to say because I don't want to take over the room. But Franco, I want to know, do you really not see that it's very obvious that the solution, the explanatory solution, is that there is an ether? Do you not see that? With the virtual photon specifically, for the room, so they know the virtual photon has to be the intermediary particle that is allowing the interaction of the electromagnetic force that holds everything together, holds all matter together. Their math didn't work. There had to be something else there that was actually holding everything together between the electromagnetic interactions. So they added virtual photons. That's why he won a Nobel Prize, because he fixed that problem. Do you see that obviously if there just is an actual background medium that is permeating all of what you're observing, that problem is solved? Do you honestly not see that an ether would fix your problems in terms of explanatory power?
No, I honestly don't see it.
Okay, fair
Are you
enough.
kidding me?
Yeah, but I mean, it's whatever.
Just
I
in
think
terms
you
of
do. I think he
theoretical
does see it.
physics, it
I think he does
works.
see it personally. So,
Like I said, he's speaking from the mainstream.
oh yeah, I mean, you can't publicly say it, maybe, but Franco, I know you're smart, and I know you do see it. But you can look at it one of two ways, and I'm actually going to fall back. I know I always say that. I'm actually going to fall back. I'm going to say this last thing to you. You can look at this one of two ways, right? One way is I've been doing this for all these years, and we have these equations. I'm not going to be like the one guy that steps out and undermines all my work or my status or kind of gets, turned on by the crowd, right? Because as Robert Laughlin, the Nobel Prize winning physicist from Harvard, right, vacuum physicist, said, he's like, we kind of all know there's an ether. We treat the vacuum like there's an ether there, but no one will say the word because it's taboo because of its historical opposition to relativity. And so you can go that route where you just like don't say the word. It's like saying hell, Satan in church or whatever, right? And you just can't say it. It's a bad word and we'll just keep using the math. Or you could be one of the guys that actually helps move society forward in our understanding. And you would compare the outcomes there. Maybe you get a little kickback for a while. You would go down in history as one of the guys that were part of the second major revolution of physics where we truly began to unify the scales. So, it's like everything worth having takes a little bit of sacrifice, Franco, right? I know you see it. Everyone knows you see it. There's an ether. It's interconnecting all of those interactions. Count it however you want to. You need to accept that there is a background. It is right in front of your face. Option A is there's a virtual photon that doesn't actually exist and we can't define it. Option B, there's something that does actually exist. It's an ether.
How are you aware that the photon is not the only particle that can be virtual? There are virtual quarks, there are virtual Ws, there are virtual Zs, there are virtual Higgs, there are virtual gluons. So quantum field theory did not stop at QED in the 40s. It went on, and now we're almost 70 years later, and we have plenty more of virtual particles. It's not just electromagnetism. There's also electroweak force. There's also a strong force. And we have all of these fields which are composing the standard model right now. So you want to call them ether, you call them ether 1, ether 2, ether 3, ether 4. For all the four gauge bosons that exist.
They would just be ether modalities, Franco. I'm trying to level with you here. Keep the names, bro. Keep the equations. I don't care. It's the interpretation that is holding you guys back. Do you not see what I'm saying to you? It's ether modalities. Call them whatever type of virtual particle you want to. That further substantiates that there's an ether. The more you guys discover, the more you have to come up with new virtual particles because there is a permeating medium everywhere. That's why you have to do that. And by the way, so the room knows, the electroweak force was ridiculed, like all the anti-flat earthers, for example, that make fun of you right now, they would have ridiculed you for bringing up the fact that the weak force is actually electric. And a Stanford professor proposed it, a physicist, they all rejected it. Everyone ridiculed how insane it is. We know the weak force isn't electric. Guess what? Now it's literally integrated mainstream consensus of particle physics. They're just going to consistently move towards everything's electric and everything's unified with the background. And they can't say it because it has implications. And let's just call out the elephant in the room. If there's an ether, the Earth can't be flying through space. That's the reason. That's the reason you guys can't say it.
I'm sorry, I totally disagree. For instance, for one thing, it's not true that everything is electric. There's also the weak. For instance, neutrinos. How do neutrinos interact? They don't interact electrically. I'm sorry, they interact weakly. How do protons and nucleons stay together? Neutrons stay together in an atomic nucleus. They stay together because of strong force, and strong force exists and is not electric. It's something that was discovered in the 50s or even before. In the 30s probably. So no, it's not true that everything is electric. I'm sorry.
Well, okay, but there are papers being proposed within your own paradigm saying that strong force is electric, but it doesn't even, I don't necessarily agree with that because you have to define what electric is, what is static electricity. Tesla said it's the ether under strain. So what's called the strong force would be the equal and opposite reaction due to the displacement of the fluid background. Word salad, the oscillatory nature of the fluid background causes emergent properties. You call them different names, including the strong force. But the point is simple. You have to come up with all these virtual particles that you readily will admit, well, we don't actually know what it is, or like Richard Feynman says, that it even truly exists. It just has to be there for our math to work, and you keep adding to it. So basically, you claim there's a bunch of particles, you find out there's a bunch of other stuff there, right, where it's not supposed to be, and you just keep making up virtual particles. It's because there is a background medium, Franco. I know you see it. This is why.
No, I don't.
What do you think quantum phone is, Franco? Franco, what is quantum phone?
Okay. Then please explain to me how this ether was predicting the mass of the top quark. Please, as when you come up with an explanation of that, it's a post-diction because the quark has been found now, but before 1995, it was predicted through these virtual processes. It was predicted what the mass would be, and it was discovered at Tevatron at Fermilab, not at CERN, and it was found. And now everyone is measuring the top mass at HC and so on. So the quark exists. I'm sorry.
It's bullshit.
The phenomena exists.
You may call it Jack. You may call it Joseph. You may call it I don't know, Mary. You call it.
Can we call it pseudoscientific time?
Call it ether. You call it pseudoscience, but it works and it predicts and it describes what we measure. That's what we care about.
Can we call it the reified time? Like
okay. You call it whatever you want. The problem is it works. It allows us to make a prediction and measure things.
Dude, this is like saying that dark matter must exist because it makes the gravitational equations work. Okay? Dark matter doesn't exist. Okay? Virtual particles don't exist. Now, in both scenarios, we have an option. We can say, okay, we're going to refuse to swallow our pride and admit that we've been wrong about our fundamental assumptions.
We don't. We don't because you say so.
Never do that.
What?
Really?
Or we stick with them, right? And we never progress. So obviously that's why there's so many physicists now that are like, okay, whatever. They're like, screw dark matter. They're like, screw dark matter. Here's modified Newtonian dynamics because we know dark matter doesn't actually exist. That's why there are so many people in the quantum realm that are dropping all kinds of new quantum field theory ideas, including ether models. At the top levels of your own paradigm, they're dropping ether models. They're being proposed every day. So
Absolutely.
It's all good. Take it or leave it. Now the room kind of knows the situation. Virtual photons, virtual particles don't actually exist. They're mathematical constructs used to balance out the equations because the predictions didn't match. It's basically the quantum scales version of dark matter. Oh, actually, as I fall back, he's going to leave. Is he still in here? Tell him to come back up so Proud can talk to him.
No,
Brad,
but
I'm sorry. I'm sorry.
this is exactly why he got nominated. Maybe he just lost connection. Who knows? But let's give him a minute.
Can you guys hear me? I feel like you guys actually answered my question. It seems like even if his oscillations or frequencies or whatever, Franco, don't run to the TL. I'm not a CERN physicist. Whatever you're detecting with your hadron collider, if it doesn't match your calculations, then what do you do? Like that would have been my question. What does he do if that's the case? Does he change the calculations?
No, they
Does he
invent
run the
something to match that up.
Well, this is what they do. Okay, so over time, they found out. So like, they keep finding where they mess up, similar to how they discovered dark matter in 1933, right? Fritz Zwicky looked through the coma cluster, was like, "Whoa, there's only 1% of the mass here." So they're like, "Okay, now we have this new concept where we'll fill in the missing mass." And so as they start to see one galaxy behave a certain way, when they see another galaxy look similar to that one, they can predict how much dark matter would be there. Doesn't really mean dark matter is there, right? It's more precise on the quantum scale because it's vibrational displacements, and they do have like insane predictive capability on the quantum scale with virtual particles, like insane precision, mind-blowing precision. There's no the phenomena they call virtual particles is a very real, reoccurring thing that we can document and measure very precisely, right? The fact of the matter is that virtual particles don't exist, though. So it's like people can't seem to separate those two things. All right, Franco's back up here. I'm actually falling back.
Witsit brought up a good point, right? When they made those predictions of gravity, they found out they didn't have the dark matter. So they invented that abstract concept because they needed it there for the math to work. Is that essentially what happened with a virtual photon?
Again, virtual photons were introduced in quantum field theory. Quantum field theory was developed in the mid, about the halfway through the 20th century, and is now the current model for describing fundamental physics, particle physics. The quantum field theory predicts. Uses a formalism which is called virtual particles. But it's just, as I was trying to explain the first time I was asked this, virtual particles appear when you are making perturbative calculations of so-called matrix elements, which are what you compute when you compute the probability for a process, for an elementary process, such as a decay of a particle, or such as a propagation of a particle, or a scattering process. You have you have rules for computing probability for a process, and then you have to make a calculation which is not possible to do analytically, on pen and paper or with formulas, and you make an approximate calculation with an expansion in some power series of a coupling constant, and in these expansion terms appear which involve something that happens between the initial and final state, which is described in terms of the exchange of virtual particles. But this is just a mathematical way of describing this, and a pictorial way that Feynman invented for both seeing it pictorially, seeing it visually, and also from that diagram that he invented.
Did we lose Franco?
As the ether.
I'm here. Did
Franco,
you hear
you
me?
Yeah, we heard you
hammered up
desperately
one.
trying to avoid Sacred's very simple close-ended question.
Simple question.
It's not a simple answer and it's not a simple question because quantum field theory is difficult. It's not something easy. You don't understand it very easily, and you don't explain it easily to lay people. It's something complicated as relativity is. It's not easy. So it's not. There's no way around it. You have to study it and to progress through the study of this by steps. You cannot explain it. And whenever you try to explain it to a general audience, there are bound to be simplifications and analogies which are then being misinterpreted all the time. It happens. It has always happened. These things have always happened. People just hearing popularization of science from even from people like Feynman, who try to popularize things and to make conferences and explain these things. And then some people would misunderstand them and think they had understood everything, and then say, no, I have a better theory, this is wrong, and so on. Feynman himself had to fight with these people. Well, he had to reply to these people. I personally translated letters where he answered people like this in the 60s. People having listened to his TV show explaining the twin paradox in relativity, and then some guy writing.
Elon with the self-snipe.
Yeah, it's all good. Just
Ether.
yeah, I mean, okay, bro. We know you know more. You could name more particles off the top of your head than us. No one's disputing that. It's like I don't need to know every single square inch of relativity in all of astronomy to know what dark matter is, to know when dark matter was discovered, and to understand the logical progression of how it was put forward. Okay. His question is just like how we had a gravitational prediction. We looked into the sky. We saw the coma cluster, Fritz Wiki, 1933. And if you can't explain it simply, you don't understand it. Okay. They looked in the sky. They looked at what we call galaxies. There was a group of them. And in order for the group of galaxies to stay together and not escape the little cluster, there was going to have to be a really strong gravitational field. But there was only 1% of the mass needed to give you that strong of a gravitational field. So they then plugged in the missing value and called it missing mass. On the quantum scale, when they were looking at the electromagnetic interaction, the intermediary interaction, and the magnitude of those interactions, they were like, wait, the math isn't working. There's something missing. There has to be something else there. They plugged in virtual photons, just like they plugged in dark matter, to make it work. That is what happened.
No, it's not like that. This is a very, very simplified way of describing this. It's not like this. It's not like it has nothing to do with dark matter. It's not absolutely the analogy is I think is totally wrong. But I'm not a theorist. I'm an experimentalist. So there's some limits to what I can discuss.
Okay, it's all good. Yeah, like I said, I was very simple. You could get much more
very simple.
You can get much more technical about the coma cluster observation. But my point is, there's a group of people here unfamiliar with it. The only reason I felt like I had to jump in is because what happens. An astronomer can come into the room and woo the audience with all these technical terms and get lost in the weeds and avoid the meta and then omit the other side of it and mislead people, right? You don't have to be a PhD quantum physicist that works at CERN to understand that virtual photons don't actually exist, that they're just a concept. That's why they're called virtual, because we never actually directly observe them. They're not an output of an experiment. We assume that they must be there because of the other effects that we see and how there must be something else there for our equations to work. Same thing with dark matter. We don't see it. It's called dark because it doesn't interact with the electromagnetic spectrum. Fancy way of saying we can't see it. It doesn't interact with light. So we fit that into our equations to make them work because it wasn't working. That is an accurate description of what happened. The reason Richard Feynman was so popular was because he had an ability to communicate the more complex ideas in a simple, digestible way. There is value to that. Okay?
I know.
And if you'll just acknowledge to the room that the way that I'm breaking it down is correct, and you would say, okay, but there's more to it, and it gets more complicated. Yes, it does. Of course it does. You know more about it than I do. The complexities of quantum. I don't need to know all of it to know what I'm saying is true. I've researched it plenty enough to know what I'm saying is true. I've talked to many other quantum physicists about it. They'll admit it, Franco. Why is it that when I talk to other quantum physicists, they happily and readily agree to what I just said?
I don't know.
He said he's not theoretical.
Oh, okay. Well, you are. You believe in virtual photons. That's theoretical. So.
Fair point. And on top of that, I heard Franco say perturbation. And hey, listen, chat, level heads, listeners, any speakers, anytime witches say perturbation, they literally lose their mind. Like, you can't say too many words that end in TION. Nah, it was just I just wanted to highlight, like, Franco used that same word too. I bet you they won't say not one thing about word salad when it comes to Franco though, when he's talking about something perturbating, right? The interesting
Yeah,
option.
that's funny.
And Franco, I don't think we're saying that we know everything, we know more. I think what we're really saying is, I think we know that we don't know, and it deserves further investigation. And if it wasn't like assumed, and you found out, hey, let's do the calculation this way, then it failed to say, oh, we need this over here to make it work. Then you put it there and say, oh, look, it works now. I don't know if that's really how that's supposed to go if you're saying that this is factual, even if the calculations may be right. And just one more thing, you said it was interesting. Now that I'm like kind of talking about this after hearing you guys go back and forth. Beautiful bill, by the way. Witsit had asked, he said, what would you need to believe in the ether? And then you said, show me the calculations I believe in. But then he started talking about like the framework and why it seemed like current science is getting away from that and wants to focus on particles and virtual particles. He said, hey, don't you see the equivalence of how this can equally work? And then you said you just dismissed it when we're just talking about the mechanics behind it, right? But then you said, if you show me some calculations, I'll just blindly believe. Well, let me not straw man you. You said, I'll just believe it if you show me the calculations. So you're really just appealing to just like numbers and stuff like that. And I know that matters. I'm not saying that doesn't matter. But simple numbers and equations shouldn't convince you whether something is reality. And I think that's the point we're trying to get past. It's good to have it to describe certain things, but you can't say that these descriptions of these values and numerals and all these different things is an explanation. The explanation is still faulty. It has a weak foundation, which is probably why it gets so complicated at certain levels, because the foundation is so weak. Now, again, this is not my field. This is your field. So I'm just listening to both of y'all build off of this, and I'm learning in real time. But it just seems weird that every single time the math fails, you put some type of abstract concept in place to make it work, and then say, look, we can make predictions with it after y'all corrected for the initial mistakes. And of course, you're supposed to do your due diligence. You're supposed to account for everything. But it seems like every time that happens, that's the way that science handles it, instead of redirecting maybe a different position or taking or looking at it from a different perspective. So,
or like re-examining the presuppositions. Like, but Sacred, I like right. You can also see why, from his perspective, it would be frustrating, right? If he's learned all the complexities of this and he does it hands-on and he's like devoted his life to it, and he knows all kinds of different little intricate aspects of it that we don't know and that many people don't know. And for someone to come say, oh, well, your fundamental interpretation of all of it's wrong, it's like instinctively is gonna be like, who are you to tell me that, right? And like, I understand that, but that's why I'm trying to, what you just laid out pretty well as well, right? Like, we're trying to show you the bridge here. We're not undermining the precision attained in quantum mechanics. It's incredible. Like, I'll be the first one to say it's one of the most incredible fields of actual science. It's experimentation. But it's the interpretation, right? And I think that realistically, all the experiments, all of your math, all of your predictability can all remain true, and the fundamental interpretations be wrong. And that's well known. And I have a feeling that if you and I were having a beer and it wasn't recorded in a public space, you would quickly agree to that. Okay, that's why they're called virtual as a placeholder. And this is why I brought up quantum foam. I'm curious what you think about that, right? Like, what is your take on quantum foam? Like, what is quantum foam?
I only know about quantum foam because I translated some books, but I don't really know about it. It's something really too far-fetched for me.
Word. So just so everyone knows, though, because you did bring up antimatter, right? Quantum foam, they claim, now, if you, like he said, the pop sci articles always say something ridiculous, which I wish the anti-flat earthers would listen to Franco here, okay? When you go repeat the pop sci articles, you're not schooling us. You look ridiculous to anyone that's even kind of researched it. But like, so the pop sci articles about quantum foam will say something like, physicists have manipulated pure nothingness, right? Okay. But that kind of shows you the flaw in their model, their interpretation, that they have to call what's in that vacuum nothingness. But it is a theoretical concept in quantum physics, and it's about basically like the creation and destruction. And I know the Ether Boys are going to find this interesting if you don't know this. It's the creation and destruction of matter and antimatter at the smallest scales inside of a vacuum in their paradigm. Okay, obviously. So it's this constant state of creation and destruction of little tiny matter, like in antimatter particles at the smallest scales inside the vacuum. So when they get as much air as they can and look at the vacuum chamber, they're like, whoa, dude, stuff keeps popping in and out of existence. And that interaction creates this like foamy quality to the vacuum. It's as if it's foamy. So that's why they call it that. It would be like if you blow bubbles and you look really close into the bubble and see it moving around, you'll see the reflections of like the bubbles. It's like they're saying that there's something in the vacuum that basically acts like that, and it's like foamy. Okay, now from an ether framework, that makes a lot of sense. A lot of sense. You know what Tesla said, Franco? Tesla said that when the ether is thrown into infinitesimal, prodigious whirls of velocity, it manifests as matter. And so that's just a fancy way of saying really small, really fast vortices, right? Little whirls of velocity that are super fast and really, really tiny. That's literally what he said. He said this in the early 1900s. He said that when it's thrown into infinitesimal, prodigious, infinitesimal means mind-blowingly small, right? That it manifests as matter. Now we have the cutting edge of quantum physics saying there's something called quantum foam, and that there's matter that is created on these little bitty, mind-blowingly tiny scales inside of a vacuum. That's actually a prediction of an ether, though. It was this incredible discovery within your paradigm because the only thing that can be there is what we can physically interact with and count. But from an ether, we were like, no. When the ether is excited, and like Tesla said, thrown into infinitesimal, prodigious whirls of velocity, it manifests as matter. And when that energy resides, it reverts back into the ether. That goes for the destruction of these particles. So now you have these matter and antimatter particles being created and destroyed on the really, really small scale inside of a vacuum chamber. That's exactly what Tesla told us would happen from an ether framework. So do you see how there is a middle ground here where you could adopt new interpretive frameworks without having to like scratch everything, every ounce of progress that's been made so far? It's not like either or.
I'm sorry, I don't. First, I want to discuss quantum foam because I'm not expert. I'm not a theorist, and this is, as you say, it's not even accepted. It's something on the frontier, such as string theories and things like that. But the point is, I cannot see your parallel with whatever Tesla said 100 years ago, because they're just words. I'm sorry, but if it's not substantiated, as you like to say, in a mathematical theory expression, I cannot understand what it means. I mean, if you don't come up with quantification and with quantitative predictions and description of phenomena, it's just words. Even the quantum foam, even the virtual particles, if you don't actually produce how they change the probability of scattering, how it is used to compute something that you're going to measure, then it's useless. Even if you talk about virtual photons, if you just talk about them and you say it's an excitation of a local excitation of a quantum field and whatever, if you don't come up with the formula for the propagator of the photon, which is 1/2 squared times g mu nu, and you have to contract it with electromagnetic currents to produce an actual probability that you can compute and then quantify and then measure, then it's just words. You need to have the theory which gives you a quantifiable and a quantified and a numerical prediction. Otherwise, it's just words.
Yeah, but just so you know, you should look into this, okay? And also, the ether boys will find this funny too. I remember one thing that they said was evidence of quantum foam existing was like stellar explosions arriving at the Earth at different rates, and since light was supposed to be constant, then one of the solutions is basically like that quantum foam characteristic, which obviously, dude, that's way off into pseudoscience. Just funny because obviously we know light's not constant, but just so you know, when you're bringing up like virtual particles, right, you have quantum electrodynamics and you have your virtual particles, and like it's pretty popular. You say it's cutting edge, just like Wheeler in the 50s proposed the idea of quantum foam, but they've been saying for like the last 10 years or so that they're verifying its existence within your paradigm again, because I think quantum foam is a stupid thing, but they're saying that because the data and predictability of the virtual particles within electrodynamics work so well together that it's evidence of the quantum foam, right? And that it also gets back into like the magnetic field strength and how it doesn't work within your paradigm, and then that's where you get those virtual particles, specifically virtual photons. When you, for example, when you add the quantum foam, then you can make like the equations and predictions match the observations perfectly. So anyway, you may not know much about it, fair enough, but you should look into it. And I just thought the room would find it very interesting, right? That Nikola Tesla said that this would happen. He said that things would quote unquote pop in and out of existence, and that when the ether is thrown into little bitty tiny whirls of vortices at extreme velocities, then it manifests as matter, but then it'll revert back into the ether when the energy resides. And so if you were to have a vacuum chamber, you would see things constantly fluctuating in and out. So the ether would be excited, go back to being inertial, excited, so like excited state, inertial state, back and forth. And that's what even their paradigm is now invoking. And, and the reason is like a lot of tests go unanswered if you don't invoke something like quantum foam. So take it or leave it. It is interesting. I'll say one more thing. I don't know if you've heard of Robert Laughlin, but that's again Harvard, and he's the guy that said the whole thing about like an ether rather perfectly describes the way that vacuum physicists actually utilize the vacuum. But people just won't use the word ether because it's so taboo due to its historical opposition to relativity. And then he also points out that, well, we now know for a fact that the vacuum is not empty and that it is not akin to Newtonian emptiness. Rather, it is filled with stuff. And when you hit that stuff sufficiently hard enough, it will knock energy out of it. And that's a Nobel Prize winning vacuum physicist, Robert Laughlin from Harvard. So these are the things they don't tell you about. These are things the pop sci articles aren't going to tell you. The anti-flat earthers aren't going to tell you. And that's why I get frustrated if someone like yourself who do have credentials, if you omit this part of it, it's misleading. Your side needs us. You need the ether. You're just crawling your way over to the ether. So, all right. I'm done.